Alright, hello. In this video we're looking at the fundamental theorem of calculus, part 2. Alright, so let's see what we're talking about here. So we mentioned in an earlier video with fundamental theorem part 1, the fundamental theorem consists of two parts. Previously looked at part 1, now we're going to look at part 2, and it establishes the relationship between differential calculus and integral calculus, or two big branches of calculus. And the idea is that what we have here are inverse processes between these two big ideas of differentiation and integration. So, looking at part 2, fundamental theorem of calculus part 2, suppose that f is a continuous function. We know what that means on the closed interval a to b. Then the definite integral from a to b of f of x is given by, or is equal to, capital F of x from a to b, where this notation just means we evaluate at the upper limit minus evaluating at the lower limit. We have to say one more thing, and that is, what is this capital F? And the key thing here is this capital F is any antiderivative of f. This is an extremely powerful tool for us. This allows us, instead of using that Riemann sum, limit of a Riemann sum definition. So before, we were looking at this business here. And some of this notation might be book specific, but it's this idea of we had a limit definition to figure it out, and you had to come up with a formula for the sum. This is very tricky business. You initiate this thinking about areas under curves, and these would be rectangles. Each one of these terms here, where the delta x is your width, and this is corresponding to the height. This is kind of like in the differential calculus when we do derivatives by definition. We look at the limit of the difference quotient, and that was pretty restrictive in terms of functions we could differentiate. Well, now it's the same idea here, where we're pretty restricted by basically these summation formulas if we wanted to find and determine the definite integral. But with this result, we can do a lot more. Finding antiderivatives is hard, but we have some practice with it, and it gives us a whole bunch more that we can do this result. So the second part of the fundamental theorem is the one we use more frequently compared to the first, and it gives us a method for evaluating definite integrals without computing limits. That's the big thing. That's the awesome part. So we don't have to mess with limits. Again, think back to the derivative stuff when you learn these rules, power rule, quotient rule, all this stuff. So you didn't have to do it by definition. That's the same, or it's analogous situation here. In terms of the connection between the two big branches, this part tells us if we differentiate a function and then integrate the result, we end up back with f. So it's kind of like we start with f, differentiate it to get the lowercase f, and then you integrate it, and you end up back with f, in a sense, because you end up with this, which is going to be a constant. But again, like before, that's what we mean. We said earlier, these are inverse processes of each other, integration and differentiation. So it connects those two big branches of calculus. So like I said, this is an incredibly useful result, but finding antiderivatives is not the easiest thing to do. In general, it's a very difficult process. It's more difficult than calculating derivatives. It's kind of like, if you think about functions, it'd be kind of like, evaluating a function versus solving an equation. Kind of getting an output versus finding an input that makes the thing true. Anyway, it's more difficult. So we know from earlier work that we've done that if f is continuous on that interval, then we know that this exists. But it may be that there's no antiderivative f, or none that we can find. So maybe that no antiderivative exists, at least in terms of something we're familiar with, let's say. So in these cases, we might do some approximation methods. That's something that you could look at in a follow-up course, maybe a Calculus 2 course. We're in Calculus 1. It's a topic that we could explore later, but we won't explore now. We're going to stick mostly with, as best we can, functions whose antiderivatives we can find. Okay, so let's look at a few examples. Here's one that you could do before. We'd use summation rule, or identity. Identity is a better term there. So you'd have to remember that, and it'd be some work to get this, figured out, and the constant part's okay, but it's a lot of work to do that. So instead, let's use the fundamental theorem, part 2, with some excitement there. Okay, so this function is continuous everywhere, so it's certainly continuous on that interval. And thinking about an antiderivative of this guy, that's the whole thing. We need an antiderivative of that. Here's one. We can pick any one we want. So if you think about finding antiderivatives, you had something like the most general, or you had that, plus c part. And we can kind of think of that as, well, let's just choose c to equal 0. Any one we want to pick will work for us. So by the fundamental theorem part 2, we know that this definite integral equals the evaluation of the antiderivative at the upper limit minus the antiderivative at the lower limit. Using this function here, capital F of 1 is 1 cubed plus 2 times 1. 1 plus 2 is 3. And capital F at 0 is 0 cubed plus 2 times 0. 0 plus 0 is 0. And so 3 is our definite integral value there. We would have got the same thing if we had done it by definition, using summation formula, limit of the Riemann sum. This is a lot cleaner, a lot faster, a lot better. Here's another example, maybe kind of a non-example here. Now this function is continuous everywhere. It's looking something kind of like this. It's going to be symmetric about the y-axis, and maybe we're looking at thinking about an area argument, something like we're trying to basically find that area. This is going to be a big problem, though. We don't have a nice form for this. It's not only that we can't find it, you can show that it doesn't exist in terms of the nice functions that we work with for an antiderivative. So this definitely equals something because this is continuous. But we don't know an antiderivative of e to the negative x squared, so we can't apply the fundamental theorem. If we knew capital F, an antiderivative, then we could apply it, but we don't, so we can't. So it equals something. If we wanted to figure it out, we'd use approximation techniques. Again, we're going to skip that. We're going to save that for later. So this is kind of a classic example of that sort of situation where you can't find an antiderivative. But we'll focus on the ones where you can. So that's our last example. That next slide there was something that I didn't really want to include. I don't know why it was there. But that's the fundamental theorem part 2. So we just did one example where everything worked out, real basic one. And we did one just to mention to you where we can't quite apply it because we don't know the antiderivative. But this is a very, 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 very useful theorem. So we get plenty of practice applying it, and we'll even learn some tools we can apply it in trickier situations for finding antiderivatives. But for now, we just wanted to introduce it, make sure we understand what it is we're talking about. And so that's the fundamental theorem, part 2.